Hello students, you are welcome back to the tutorial video on Lebesgue measure. In the previous video we discussed the set of intervals. We have discussed the characteristic functions. We've discussed the step functions. We've extended the concept of Riemann integral with respect to Lebesgue integration. Trying to draw the difference between the two. Now, we want to continue from where we stopped before. In the last statement, we have if f is a bounded function defined on an interval a, b, and if f is not too discontinuous, then the Riemann integral of f is defined to be the limit of the integral, the Riemann integral of f. The Riemann integral of f. Let's assume that this is the Riemann integral of f. Of f is defined to be the limits of the integrals of the step functions, integrals of the step functions which approximate f. Let's say this as n tends to infinity. So you could see that the Riemann integral, you see the connection between the Riemann integral and step function here. Okay, now we said in particular the lower Riemann integral, this is the lower Riemann integral of f, this of f of x is may be defined to be the supremum of the integrals of all step functions, integral of all step functions, such that the step function is bounded by, because it has to approximate like we have said in the previous statement, that is that f is defined to be the limit of the integrals of step function which approximate f. So is bounded by f. Okay, now and it is when x is in the the domain of our dimension a, b. But if x is not there, don't forget the step function of var pi of x will be equals to 0. Okay. Now let's continue. Let's continue. Now, the Lebesgue integral can be obtained. The Lebesgue integral can be obtained in the same manner. Can be obtained in a similar manner. How? You're going to see that now. All similar process, except that the collection of step function can be replaced by a broader one of step functions is replaced by a larger class of function, Now, what we said here is simply that we saw how we can relate Riemann integral to step functions. So we could equally draw that line, but the only thing is that doing that for Lebesgue integral would be disastrous. Would be an error, because the Lebesgue integral is an integral taking on a bigger class of functions. It's more than, in terms of the domain of the division, like I told you, is bigger in class than the Riemann integration. So it's going to be the what? For us to follow that line by relating the Lebesgue integral with step functions, it creates a lot of problems. So what will happen is that we need a larger class of functions. When we get there, that class of functions will be simple functions, because for us to define the simple functions, the collection of subsets, that will stand as the domain of that dimension must be what? Must be measurable, because the simple function itself is defined on measure space. Okay, so there will be difference when we get there. We differentiate between measurable space and measure space. Measurable space, has two components, while measure space has three. So when we get there, we discuss more about that. Okay. Now, furthermore, the notion of length is generalized to a suitable collection. Now, want to generalize the notion of length. We have seen the length of interval the other time. So now we have started. We are bringing up idea of extending Riemann integral to Lebesgue integral. So we started the concept of Lebesgue integration now. So now we want to discuss the notion of length. So furthermore, the notion of length can be generalized. Of length is generalized to a suitable collection of subsets. Let's use this to designate that subset of subsets of R. Don't forget, those intervals are subsets of R. Once this is done, the step functions are replaced by simple functions. The step functions are replaced by simple functions, okay, which are finite linear combinations of characteristic functions of sets, belonging function of sets belonging to A. This A is a collection of subsets. Our A in this concept, is measurable. Is a collection of subsets of R. So you can see that because of that, now we have to operate with simple functions, which give us a broader class of functions, a larger one than the step function. So now, if our step function, from 1 to n, is such a simple function, as every step function is a simple function, and if measure of the set E denotes, that is, mu of E denotes the measure or generalized length. Remember, we want to generalize our length, so we introduce the measure, okay, of the sets E in a class of subsets of sets. In a class of subsets of set R, we define the integral of our step function to be what? The integral of our step function now will be defined this way: sigma Cj of that is measure of EJ. J is moving from 1 to N. Now you could see the interesting thing here. You could see how we have how we have generated a generalized length from a smaller length, which was associated, well, which is associated to the step function. Now don't forget our EJ is an interval of length, in R. So, and this chi EJ is a characteristic function of EJ. Okay. Now don't forget also that E is a cover to what? EJ. I hope you understand what I mean by cover. Fine. So it implies that for us to generalize the length of the measure, since we are introducing a larger class of functions, we are no longer discussing we are no longer being restricted to step function. We want to introduce we are introducing a general class of functions because we want to generalize our length, because we want to expand beyond the scope of having just a very small length of the interval with respect to Riemann integration. Now we want to go into discussing the concept of Lebesgue integration, and for us to do that, we have to discuss a broader or larger class of functions. So you can see how we relate, how we connect the step functions to the simple functions. You can see the difference. Okay. So if f is a non-negative function defined on R, if f is a non-negative function defined on R, which is usually restricted, we shall define, can you see now, the Lebesgue integral of f to be the supremum. So let's quickly write that and see how we are gradually coming to the Lebesgue integral. You can see how we are gradually coming to. So if f is a non-negative function defined on set of real numbers, which is usually restricted, we shall define the Lebesgue integral, you can put it in brackets, integral of f, to be the supremum, of what? Of the integrals of all simple functions. Interesting. All simple functions. This is different from the Riemann integral. Such that that pi of x is bounded by, because we want to approximate the function itself for all x in a set of real numbers. Okay, so the integral can be extended to certain functions that take both sides. So you can extend it to certain functions that take both sides. That is, whether it is negative or positive. So let's try to stop here for now. We don't want a very long video, so we continue from here in the subsequent video. Stay blessed. Don't forget, click on the notification button so that each time I produce a new video, you'll be daily notified. God bless you.